because having heard Umesh, you will feel, I'm sure, disappointed in my lecture. So anyway, thank you, sir, for being with us. So I'm happy that there are faculty members here and also students. Already 15 minutes are over, so let me not waste time. And yes, yes. So I will start with my lecture. So the title, as I told you, is Quantum States of Light. Maybe Professor Umesh will also tell more about it after my lecture, as he told me. So it all started with blackbody radiation. Max Planck in 1900, he said that oscillating systems which are in the walls of a blackbody cavity, they oscillate with frequency nu and they absorb and emit energy in integral multiples of h nu. It was a bold idea. He used it to explain the blackbody energy distribution. Lummer and Pringshim got the curve experimentally that you see, this red curve. Wield's classical description agreed only at lower lambda. So you can see the blue curve. Mic is on. So Wield's theory or theoretical formula agreed with the experimental curve at lower wavelengths, but failed at the higher wavelengths. You can see the red curve is the experimental one, and the blue curve, I think, is Wien's curve. It slightly varies. It almost explains blackbody spectrum. However, since it did not explain completely, Rayleigh-Jeans gave, again using classical physics, an idea using statistical mechanics and all that, and their curve, the green curve, agreed at the higher wavelength, but failed at the shorter wavelength. In fact, at that time people told that it led to ultraviolet catastrophe, which means you just take any body, heat it to certain temperature, you get all that you want, right? X-rays, gamma rays, everything. However, this experimental curve could not be explained by either Wien or Rayleigh-Jeans. Planck made this bold hypothesis. Using that, he came out with his own expression for the blackbody radiation. So his formula agreed with the experimental curve. So this is how the idea of quantization came right in 1900. In fact, we say that Bohr started earlier, but it was a quantum jump was given by Max Planck. But then let us look at the first statement. He said that oscillating systems absorb and emit energy in multiples of h nu. What I mean to say is, the meaning of this statement is, material of the black body has quantum nature. He did not tell about the radiation itself has that nature. It is something like we drink water. So water is everywhere, but we take maybe like 1 cup or 2 cup. So it is our exchanging with water is discrete. Not that water itself is discrete. In fact, I think Planck was not happy if when somebody said that have you quantized light or so. He said no, the oscillating system exchange of energy is discrete. It was Albert Einstein who said that, let me assume particle nature of light. The energy of light comes in integral multiples of h nu. He could explain the photoelectric effect using this particle nature of light. Later, a chemist, G.N. Lewis, named it as photon, the particle of light. So the credit goes to chemist, but the physicist Albert Einstein made an extraordinary attempt by using this notion that instead of saying that not the walls, even the light's energy is quantized, he could explain the photoelectric effect. So is photoelectric effect due to photons is a question one could ask. In fact, Einstein was given the Nobel Prize for describing photoelectric effect with the notion of photon. W. Lamb Jr. and M.O. Scully, they used quantum mechanics. They also used time-dependent perturbation theory, which is called semi-classical approach. Using this, they tried to explain the photoelectric effect. What I meant to say is, they started using quantum mechanics, and let me come later to how they actually did it. This work does not figure prominently in the history of quantum mechanics. I mean, in the broad light of Einstein's idea that photoelectric effect can be explained using particle nature, perhaps this was shadowed a bit later. Let us first note the observations in the photoelectric effect. When you say I have explained photoelectric effect, how does, the explanation come? So in order to see that, let us look at the observations in the photoelectric effect, and also let us see how Einstein explained using photons. So first observation in photoelectric effect is instantaneous emission. As soon as light falls, electrons come out. So you can see the figure and the graph. Next, intensity is more intense light you send, more electrons will come. So you can see a less intensity, only 2 electrons are coming, higher intensity, more number is coming. So you can also watch the graph. Next, threshold frequency. That means if you send a lower energy light, photoelectrons will not come, but if you send higher energy light, photoelectrons will start coming. Therefore, there is a threshold frequency beyond which the electron emission occurs. Lastly, high frequency. Suppose you use blue light instead of green light. Blue light has high frequency. You will see that the electrons will move faster. So in order to arrest them, you have to need higher voltage from the negative side. So the stopping potential is proportional to the frequency. So Einstein used this equation. How did he explain using particle nature? We have studied this, but as a review, I am taking this. He said h nu equals 5 plus mv square by 2. This is the great equation by Einstein. Photon, a particle carries energy h nu, it hits an electron. This hitting is like a billiard ball collision. So you can also see in our classical domain, if you hit one ball with another ball, the transformation or the transfer of energy is quick. Momentum is quickly shared by the other one jumps quickly. So by this he was able to explain the instantaneous emission of electron. Secondly, maybe here it is saying that electron absorbs this h nu minus phi and comes out. This phi is the work function. It is inside the metal and it has to come out of the metal. It needs certain energy for this. Next, intensity increases means he said photon number increases. Therefore, as photon numbers increases, they can eject more electrons. So that is his explanation. H nu less than 5, that means the energy of the light is not enough for the electron to come out of the metal. Therefore, electrons don't come out. Frequency high, kinetic energy of the electron will be high, because as soon as the work function is over, all that additional energy given by light is used for moving. So electrons move with higher kinetic energy, therefore you need large potential to stop the photocurrent. This is particle nature used by Einstein to explain photoelectric effect. So these are the 4 things. So photoelectric effect without photon picture. Can we explain photoelectric effect without this picture? Lambert and Scully did this. They used this semi-classical theory. Maybe this phrase may appear strange, no, but you are already studying. Those who are in second year MSc or so will be studying time-dependent perturbation theory. This is just a case of that. Semi-classical theory means atoms are quantum system, radiation or electromagnetic field is classical. So atoms have discrete lower energies followed by a higher continuum of level. That means these higher continuum levels are nothing but the ionization levels. As soon as you excite the electron beyond those discrete levels, the electron comes out of this atom. Electromagnetic field is classical. So atoms are treated quantum. Electromagnetic field is classical. This is semi-classical theory. Pure classical theory, both are classical. Pure quantum theory, both atoms and fields are quantum description. So according to them, electric or electromagnetic field consists of electric vector. This electric vector, say, is along, it's moving along z-axis and polarized along x-axis. It is given by this EFRT. So field variables are C numbers, atom variables are Q numbers. That is what we mean by semi-classical theory. C numbers means at best complex numbers are real numbers. Q numbers means operators. So atom interacts as a dipole with electromagnetic field. When there is an atom in the neutral state, the positive charge center and the negative charge center will be at the same place. As soon as an electromagnetic field passes through them, the electric field will separate the charge center. So there will be positive charge center here and negative charge center here, by which an atom behaves like a dipole. So this dipole interaction will take place. That is the potential for this interaction, minus Ex EFT. I have assumed a simple picture, right, in order to show that even this semi-classical notion or semi-classical treatment where you treat light as a wave, right, that also explains photoelectric effect. So Fermi-Golden rule you derive, and that means how many transitions occur, what is the transition rate with respect to time, how does it change with respect to time, etc. It is given by this XKG matrix element. This matrix element is one important contribution from quantum theory. I think quantum theory has got three concepts which can be tested experimentally. One, I think, is the eigenvalue, right? So you know the notion of eigenvalue in quantum mechanics, that can be tested in practical. The other one is the average value. So expectation values can be tested experimentally. And the third one is this matrix element. So matrix element square gives the transition probability, and transition probability is related to cross section. So these are the three things which connect the quantum theory to experimental theory. Perhaps the success of quantum theory lies in the fact that all these find, correct explanation according to experiment also.
Yes. So, through the Fermi-Golden rule, they have introduced quantization.
For the atoms.
For the
atoms only.
But EK and EG have nothing to do with E in the first step.
They are the atomic energy levels. Here is, so ground state is EG, EK, etc.
So V equal to EXE, that E is different.
That is the electric field. Right. That is the classical electric field. So this pk of t, transition probability, how many transitions occur, right? Till Ek, in this expression you can see Ek minus Eg minus H cross omega in the denominator as well as in the numerator. This, if you plot a graph, it will be a very big peak at the value Ek minus Eg minus H cross omega equal to 0. That is called the resonance situation. Outside that, it will fall off sharply. So, peak.
Sinc function.
Right, sinc function. You can see like this. You draw this in any time-dependent perturbation theory discussion. So, till Ek minus Eg is equal to H cross omega, no transition. So, there is a threshold. Only when Ek minus Eg is equal to H cross omega, there will be resonance. And if you supply higher, frequency light, then the resonance occurs for the further levels. Therefore, transition occur after this level. For each k, you have a certain resonance condition. So transitions occur. So that is given by this. So as this particular expression explains one of the observable factors, that is, there is a threshold, right? Until and unless the energy of the photon matches with that, there won't be any transition. This is an experimental observation proved by Lambert and Scully using semi-classical theory. Next is pk of t is proportional to E naught square, as you can see in the formula. E naught square is the intensity of electric field. So therefore, more intensity, more transition. So the second observational factor in the experiment is also explained by this Lambert-Scully idea. So as frequency increases, the electrons gets into higher and higher energy levels in the continuum, which means they will move with faster kinetic energy. So that is also explained using this. So ejection of electron is due to transition to all state, not just one state. So in which case you will have to sum over this expression that integrated probability increases with t. So as soon as the light falls, electrons start appearing. Maybe I may be not very accurate here, but this more or less says that the transitions occur right from the beginning, say from 10 power minus ninth of a second and all that. Therefore, I wish to say that rather, the book which I refer to has said that all the four experimental observations are explained by this. Einstein's explanation was this. Rather, this is the my title is wrong. This is the explanation of photoelectric effect using Lamb and Scully idea. So it looks like was Einstein wrong? No. What Lambert Scully is saying is, no, you explain photoelectric effect using particle nature. We are explaining it using wave nature. So you are also right and we are also right. So it is some sort of a win-win situation. Like then what to understand from this? I always as a student I used to do chemistry lab where we are supposed to find some new radical. But before finding the new radical, we would do some preliminary test and there would be a final confirmatory test. Only from that we could say this is the compound or this is the radical which we wanted to see. So it looks like Einstein's theory and Lamb and Scully wave theory both are like the preliminary test now. So which means that so if you listen to Einstein, he will say light is particle. If you listen to Lamb and Scully, they will say light is wave. So I mean, after all, what is light? Where is the photon here? So is there any firm ground for photon? Is there any confirmatory test for photon? Hope I mean I want you to question me if you can't understand my way of telling it, right? So do you agree with me that there are two approaches now? One approach supports particle nature, the other approach supports wave nature, but then therefore there is a need for, if there is a photon, which experiment will decide that there is a photon? That is the question for which we are led to. So photon means indivisible particles of light. So we need a confirmatory test. So how to detect if there is a photon? So let us use our common sense. A wave, we know, it extends over a large region. So those of you who have seen waves in a sea or in a river, it extends from left hand to right hand. So if somebody asks you where is a wave, you will say, so wave is here also and wave is there also. But whenever you are talking about a particle, it is either here or there. So whereas a wave is here and there, a particle is here or there. So there is this. I mean, you need not have to go to a high research physicist to distinguish between wave and particle here. Any common man will also agree with that preliminary notion for that light. So this distinguishing property can be tested with modern detectors. Maybe at the time of Einstein and all that, maybe there were no good detectors or there were no detectors. Now I think my lecture is already, whatever lecture I am giving, I mean people who have found out photon detectors may laugh at me that you are talking about 3 decades instrument. We have new instruments already. There are single photon detectors. Maybe Professor Umesh might have mentioned that to you. But I am just taking you through the story of how this photon picture finally got into the scheme. So so if this is the distinguishing property, keep two detectors at separate places. One detector here, another detector there. Then send the same source of light to both of them. If both of them don't click at the same time, that means light goes to one or to the other, right? Light has gone to this detector or it has gone to that detector. So that indicates particle nature. Simultaneous clicking, suppose both of them click simultaneously, then that supports wave picture. You may also say, in fact, Feynman says in his lecture, right, when suppose two detectors in the two-slit experiment detect at the same time, what do I understand? He is looking at the electron interference experiment. He says that did the electron divide itself into two and half went to here and half went to there, therefore we got a simultaneous click. So he raises this question and later says, no, I can understand if it has become half an electron in either detector, the sound cannot be that much. So it will be click only, not click. So that can tell me whether the electron has divided or not. So that is removed even here also. Either you see a full click, no question of half click. So what is an experiment that can decide this? A simple experiment is this. You know that there is a beam splitter in Michelson interferometer, you use it. So if you send light through the beam splitter, it is a 50-50 beam splitter. I am struggling to write. I am interested in writing matrices for polarizers, retarded wave plates and others. I am still struggling to write what is the matrix for a beam splitter. And the difficulty arises that there are what are called 50-50 beam splitter and there are also what are called polarizing beam splitter. Experimentalists are very, one must appreciate their intelligence. What I write is maybe for the non-polarizing one. For the polarizer beam, what should I do? I don't know. I mean, youngsters can help me. I can share whatever I have done in that direction. So a 50-50 beam splitter splits any intensity I into I by 2 this side, I by 2 this side. One goes to detector 1, the reflected goes to detector 1, transmitted goes to detector 2. So take a light source with a collimated beam of intensity I, light falls on a 50-50 beam splitter, reflected light goes to D1, transmitted light to D2. Each detector detects I by 2 on an average during some interval, say some 1000 seconds. So you have to do experiment for say 1000 seconds. Let us study the responses of both the detectors more closely. So how they respond. So how to understand their response, right?
What is the nature of incoming light? Is it continuous light or pulsed?
Well, it is done for 1000 seconds. Initially, it was a continuous beam, right? So,
I was wondering
uh,
that you are going to tell us that photon is the light that is goes horizontally or vertically.
yeah, sure. Right now, I don't know. I mean, at some point, I will start doubting about the light itself. So I request you to kindly wait till then. So now I am doubting about how does a detector respond. So simple, it says it gives a click. That is all. What is there? What is more there to understand? So you may say each detector responds with a click. So when it clicks, what does that mean?
No, I have a problem
Huh,
because if I am having a continuous beam,
huh,
both detectors D1 and D2
huh.
will keep showing me one signals continuously.
Huh.
Where is the click?
Maybe, right? What I mean to say is, these clicks may be for the detector counts, but finally for that it may be a meter showing, this number of count. You are talking about whether we are having counting detectors or intensity measuring devices.
In short,
Huh.
are you going to tell us something where the incoming light is very few photons later?
Yeah, why not? Why not tell later? Right from the beginning, I will say we will use dim light. In fact, I did not write it here. Maybe somewhere in the end, I have written. Thank you for telling this. We should use dim light only. So, assume that we are using dim light. So, coming back, each detector responds with a click. So when I say click, click does not necessarily imply that light is quantized. When it clicks, say suppose a detector click, does that mean that light is quantized? So detector's response for arrival of light is to give the click. That light has come to me. That is given a signature through a click. That's what I mean by a click.
What happens in a detector is
Ah.
photon comes in into the semiconductor. It will generate one electron hole pair. So you could say one click is one electron hole pair.
Yes, you are already assuming that there is a photon coming. The problem starts with we don't assume whether it is a photon or a wave. So we are just starting with the preliminary notion of when we say a detector clicks, the click is a signature of the arrival of light. So it 1 minute. What I mean to say by that is once light comes, there is a certain process that goes on inside the detector, and ultimately the after that process there is an end result. That the end result is the click. Right? That's what I mean by this. So it is the detector's response for arrival of light, or detector's response for arrival of light is to give the click. So to correlate these clicks, suppose D1 gives a click and D2 gives a click. So to check whether they are simultaneous or not, I have one coincidence counter which says it will record or it will give a click only if both D1 D2 click at the same time. So if D1 D2 give the click at the same time, then CC gives a click, then I can understand that the light has, arrived at both the detectors at the same time. So let us study the clicks of all. So let us look at the nature of clicks, how to do that. So if light has particle property, now photon either gets reflected to D1 or transmitted to D2. D1 and D2 do not respond at the same time, right? Therefore, CC does not click. So, if light consists of photon, then either the photon is reflected or it is transmitted. If it is reflected, only D1 will count. If it is transmitted, only D2 will count. Right? Since both of them cannot happen for the same photon, so either you see D1 clicking or D2 clicking. Therefore, CC will not click. If light has wave property, then the light divides equally at the beam splitter. The two wavefronts reach both D1 and D2. D1 and D2 both respond at the same time, so CC will give a click. So if you get simultaneous clicking, that supports the wave nature. If the CC does not click, then it's a signature of the particle nature. So I hope this will at least satisfy you. We are still doubting what is light. So this is the kind of hope, or rather, this gives a way of checking whether the light is particle. So to decide about light, a quantitative measure is needed. So not a qualitative way of telling this. So how do we give a quantitative measure? Let us say P1, P2, PC be the probabilities of clicking of D1, D2 and CC. So P1 is the probability of clicking. Probability of clicking means number of trials, total number of trials, and the number of favorable trials. Number of favorable trials divided by total number of trials, that gives the probability P1. So we define anti-coincidence parameter. This is the quantitative measure. This is given by PC divided by P1 into P2. If light consists of photon, D1, D2 will never click simultaneously. CC does not click. Therefore, PC equals 0. Therefore, A equals 0. So, if in the experiment you get a situation and if you calculate A and A turns out to be 0, then that supports the photon picture. If light has no particle property, say wave property, then D1, D2 click simultaneously, then PC will not be 0 and therefore A will not be 0. So non-zero value of A supports the wave nature. There is a third property which they have said. They said that suppose D1 and D2 simply click randomly. So whether there is any correlation between arrival of light and their clicking, suppose we don't know. We are not very sure about their random clicking. So their clicking, it is random, say. Then if they click randomly, if there are two events occurring randomly, the probability that both of them happen is given by the product of them. So probability of both two random events occurring is given by the product of the individual probability, which means PC is equal to P1, P2. So if you put PC is equal to P1, P2, then A will be equal to 1. So there are three situations. So one is concerned with particle nature, second one is concerned with wave nature, and the third one is concerned with the nature of the detectors, right? So whether the detectors are detecting randomly or in a very
P1, P2, would it not be the randomness in electron hole pair generation?
Oh, maybe I have not yet come. I will come to. I mean, you are talking about the structure of the detector and how it is happening. Yeah.
It's in the detector.
Yes. Yes.
So
So I will come to that. Maybe I will again come back to this, which may help you, because instead of probabilities, I will talk about the numbers.
So right now we are looking at three options.
Yes.
A equal to 0.
Yes.
A equal to 1.
And A not equal to 0. The first option supports.
A being something different from that.
Yeah, of course, the third one and second one, they belong to one class. A is non-zero, right?
Yes.
In the second. The first one is belonging to one set. So this one clearly support the particle nature. The other one support the wave nature, the other one talks about the detector's behavior also. Maybe right. Is it X NAR gate? Right. Maybe you are right. AND gate. Yeah, you are right. XOR will respond when 0 and 1 case. XNOR will respond 1 1, but 0 0 also it will respond, so it cannot be that. Okay, so experiment is done for say some time t. Now I am looking at detector. Maybe Professor Umesh will find some reason here. So how do we understand the probabilities for the detector? So experiment has to be done for some time t, say 1000 seconds as I told, but there is a resolution time delta tau for every detector, for any detector, and I mean under the sun. What does it mean? D1 and D2 both need some delta t time, sorry, delta tau it should be. I have written delta t somewhere. So delta tau to produce a click. So which means that I think those who are in nuclear physics, they know this is called the dead time of the GM counter also. Suppose a particle comes and GM counter is trying to see that particle. Within that time, another particle comes, then that particle goes undetected because the detector is more concerned about looking at this thing. Maybe like some human behavior. When some VIP has come, the other VIP might come so quickly, but we will be only looking at the first VIP also. So that resolution time, maybe I'm using that bad example, but detectors do have certain time because they have to prepare themselves. Something has to happen there. So CC also needs this time to click. CC is not different. I mean, it's also a detector. It should also have some resolution time. So if signals from D1, D2 come within delta t, so when does CC detect? I said CC will detect when both D1 and D2 click simultaneously. But suppose D1 clicks and D2 clicks after, say, within next to delta tau, which means there is no coincidence, but for CC it is coincident. So hope I mean what I said is understood. So if two signals come and their time difference is less than delta t, CC will assume them to be simultaneous because that is the resolution time for that CC. So let us count the clicks N1, N2, Nc in D1, D2 and CC. So these are the counts, say number of opportunities. How many opportunities you have given to each detector? That I say is given by capital T divided by small delta tau. So something like say 1000 seconds is my experimental time and resolution time is 1 millisecond. It is 10 power 6, right? Last night I had written 1 microsecond. I suddenly had to change, right? Early morning I see I have written mega as micro. So it is 10 power 6, I agree. So 10 power 6 opportunities are there, possible opportunities. So what is Pi? Sir, Pi is number detected by number of opportunities. So this is Ni divided by T divided by delta T. I had to put this slash because if I put T divided by delta T, my last equation goes below the view. So some exercise had to be done. I was wondering whether my last equation would be last. In several lectures that happened. especially for our Professor A.V. Gopal Rao. He would prepare such a nice transparency. Half would go off the screen and he would always find why it always happens to me was his regular comment. Anyway, let me not waste time. So, if you put, suppose there are 100 counts, say, on an average. So, Pi, each detector probability is 10 power minus 4 because Ni is 100 divided by 10 power 6 is 10 power minus 4. Pc is Nc divided by the same thing. So, this A now, the anti-coincidence parameter becomes Pc over P1 P2, which is Nc over N1 into T by delta 2. So, Hanbury, Brown and Twist did this experiment. So, as a lecturer during my initial days, I was reading optics. I was stunned at not this experiment, the experiment which Hanbury, Brown and Twist did it. Maybe I will take 2 minutes to explain that. They got Nobel Prize for that. So why it was worth a Nobel Prize? You have heard about two-slit experiment and Michelson interferometer. Michelson interferometer experiment and two-slit interference experiment, they look at the correlation between electric field at one place and electric field at another place. This is called spatial coherence. Then in Michelson interferometer, you look at electric field at one time and electric field at a later time at the same place, because this goes and comes here, this goes and comes here. Suppose you change the path difference, this will come later. So you are comparing the coherence between electric fields at two different times. This is called temporal coherence. Laser light has got larger temporal coherence. That is why you can see more fringes for laser light. You can also do electric field at one place one time, correlate with electric field at another place another time. In your two-slit experiment, if you consider the screen, the exact midpoint will refer to something like same time events. But if you consider any other point in the screen will refer to correlation light from this and this. They come at different time and also they are originating from different places. That is called mutual coherence function. These are complex functions. So there are experiments to measure the magnitudes of this. However, there are less number of experiments to determine the phases of this. There is a book by Klaver and Sudarshan. It is, I think, Quantum Optics is the name of that book. Interestingly, and so I was excited to see that book not in our central library, in Mysore city central library. So nice that I went there. At that time there was, to get it xeroxed, it was so, I had to lend the book and the librarian sent an attender along with the book and I had to get it. There are 3 rupees per page or so, I still remember. Anyway, Hanbury Brown Twist experiment, they got the Nobel Prize because in their experiment, they correlated intensity in one place at intensity with another place. So, not the electric field, it is the square of the electric field intensity. So, that is why they got the Nobel Prize. And more significantly, this interferometry is used in astrophysics. You collect starlight at 2 different interferometers and find out some of the interesting properties of light. Anyway, Hanbury Brown Twist, this experiment I am telling you is almost similar to that. So let us come to this. They used Sir Mercury light. That is why I was, when you said what is the kind of light they were using, at that time they could use only mercury light and that to 435.8 nanometer. So it was chosen. Filters use it to stop any other wavelengths, like you can see in the picture. Experimental result came was A is equal to 2. So this was the experimental result. So did not support the photon picture, because photon picture you should have got A equal to 0. Not a random picture. If randomness was right, you should have got A equals to 1. Right? No simultaneous clicking. If simultaneous clicking is there, then A should have been something like some 10,000. Why it is so? Because NC will be NC by divided by N1 N2 into T by delta T, it turns out to be 10,000. So neither it was 0, nor it was 1, nor it was 10,000, it was 2. Right? This experiment really baffled the people at that time. That is why I have also put it in big, so that even if my lecture goes, you will remember that big A is equal to 2. So why the unexpected result? Is the result due to detector behavior? So how do they respond? Will the response explain the result? So they started not now worrying about what is late. They wanted to see, let us try to understand this result. First, let us explain the result. Later, let us explain about late. That was the problem. The problem got shifted to this situation. So maybe they need a warm-up time for first and subsequently. So once there is a click, they need certain warm-up time for to do the next click. As light enters, warming up builds. After sufficient build-up, detector clicks. You may say photomultiplier tube, as Professor Umesh perhaps was referring to. So when light comes, you see some photoelectron being ejected at one place. They are directed to another cathode and they cause some other more number of photoelectrons. Again, this cascading occurs and finally that goes to the detector. So this cascading is the time needed for finally, registering the signal. So detectors, suppose both the detectors are in identical condition, warming up is same, both click together, so they get I by 2, I by 2, therefore in intensity, so NC will be equal to N1 is equal to N2, and so A will be 1 by P1. And if you assume this kind of behavior for a detector, then you should have got A is equal to 10,000 or so. So you did not get. Suppose you say detectors take different time. Maybe one of them is, to begin with, it is already energized by some, for some reason. So the response will be not, simultaneous. So in this case, A should be 0. So if you look at the behavior of the detector in this way, in other words, this is a classical notion given to the detector. It responds, say, according to this classical picture, it needs a warming up time and all that. If you use that, even then you cannot explain, because this calculation tells you either A should be 10,000 or A should be 0. So the classical detector behavior is not supported by the result.
By the way,
Yes, please.
have they done experiments with detectors cooled down to near 0?
Oh, regarding that, I'm not, this, even while describing this, they do not give us exact description of what the detectors were and how they were maintained. Their idea was to tell more about how these experiments, finally.
You say two detectors are identical.
Huh. Yeah.
Room temperature. What is the guarantee that they are?
Yeah, right. No, this is, if they are identical, it should have been this. If they are not identical, the other would have been this. So by using whether they are identical or not, they thought whether we could get the experimental result. So neither way, neither identical nature nor non-identical nature helped them. Therefore, they had to go beyond this classical model for detector. So alternative choice. Then this, now I hope you also, I hope you are following me. We are sidelining the issue of whether light is particle or not for the time being. We are worried about the experimental result. So let us see whether we can explain this. So is there any alternative choice? Yes, detectors are not classical, but they are quantum detectors. See. So Professor Umesh is already, trying to say, what do you mean by that? Right? So I appreciate, why I said this lecture, I haven't seen it. Yes.
You already mentioned that the atom is quantum.
No, that is theory, Lamb and Scully theory for that. Now it is in the experiment, they are meeting the detectors and they are saying that the detector are quantum mechanical, and exactly they follow Lamb and Scully arrangement. So time dependent perturbation theory has to be applied for detector. Why that has to be applied? Because the detectors have energy levels. They are, well, how do they detect? Light comes here, and say the detector has atom, they get excited, and that excitation may later give some de-excitation, and that signal may travel to the detector. So they have energy level, and they respond by absorbing light and getting excited. So the atoms in the detector. Probability of clicking depends on time arrival delta t and the intensity of incident light. If that is the case, then the probability of detection by any detector is proportional to the incident intensity of the light as well as time during which you are allowing them. That is why P1 is proportional to I delta t. That I is the intensity of the incoming light. Delta t is the time duration. So more time you give, more detection. More intensity you send, more detection. Therefore, like the radioactive situation. P2 is also proportional to I delta t. So for some reason I have taken alpha 1 and alpha 2. Maybe some other internal differences could be there between the detector. So what is P1? Alpha 1 into I delta t. What is P2? Alpha 2 into I delta t. They receive the light and they respond. So this is first order perturbation theory. This is the expression for P1, P2. How about for PC? I will just complete. PC is looking at the combination of these two. What is the probability of PC? So that has something to do with P1 and P2. Therefore, it is connected with, it is proportional to I square and also delta T square. So it is given by actually P1 into P2. So if you substitute that, you will get A is equal to 1. So even if you assume that the detectors are quantum mechanical detectors and they are detecting by excitation and all that, even that idea fails to give you the A is equal to 2 result. You get A is equal to 1. Yes, sir.
But Heisenberg's uncertainty principle has not yet been, because any transition, it should probably value delta E delta T of the order greater than epsilon. This delta T we have written.
The delta T is the time given, right, for the detection. So if you, delta T is not fixed here. More time you give for delta T, more will be the detection. I am just looking at how to define probability, or how does first order quantum or time dependent perturbation theory give values for, or give expression for probability. This is from that main formula that we wrote. So if you assume that the detectors are quantum devices where atoms excited and thereby detection takes place, you will end up with the result that A is equal to 1. So no use, right? So what more you can say? Detectors are quantum. Let us stay with that. But light intensity may be fluctuating. So now you started, okay, there are so many things in the experiment we have to suspect. First, our aim is to find whether light is photon or wave, but there are devices about which we suspected. First we thought they are classical devices, it did not explain. They are quantum devices with atoms exciting, that also not explaining. So the next thing is there is light, let us suspect light. So how do we suspect? We said that P1 is proportional to intensity, P2 is proportional to intensity. That intensity is always changing in time. Well, he says, why? Let me take this screen itself. Is the intensity changing? I hope you will, no, I will explain to you by asking the question. The intensity appears to be constant. But what is seen is nothing but light. It consists of electric field. My explanation to that, why is Professor asking is, this E electric field, whereas at this visible range at a frequency 10 to the power of 15 hertz. Maybe you referred to that or you are referring later. Right? No, I will complete that. Right. So 10 power 15 hertz. So this intensity will also be oscillating at the same frequency, 10 to the power 15 times per second. When we blink, our blinking takes 10 power minus 3 seconds. So 10 power minus 3 seconds is 10 power 12 times larger than the frequency of this. So when we look at, by that time, it would have, 10 power 12 times it would have, oscillated. Therefore, what we see is, though there is a time varying intensity here, what we see is an averaged intensity. So ordinary light comes, this light that we getting is actually varying in time, right? But that variation is so far. Thanks God that it is so far. If our eyes were able to respond to that time, suppose we had femtosecond, or what 10 power minus 15 is femto, femto. Suppose our blinking was 10 power minus 15th of a second, I would have seen variation of light intensity here, and I would not have seen you at all in this form, right?
But so it could have been a periodic variation, not fluctuation.
Yeah, that means fluctuation in the periodic variation is a form of fluctuation, a very systematic, coherent way of fluctuation, right?
What I was trying to hint at,
Okay.
light is also generated by semiconductor source. Detector is also a semiconductor source. Both should have the same kind of randomness in.
Yeah, right. So anyway, so this is regarding the way we consider the electromagnetic field, that whenever we say a beam of light, that beam of light appears to be constant for us, but there is oscillation of the electric field which causes this intensity, time varying intensity. So one should use the average intensity I instead of instantaneous intensity, and average of I square instead of I square. So if you use that, P1 is alpha 1 into average I delta t, P2 is alpha 2 into average I delta t, PC is alpha 1 alpha 2 average of I square into delta t square. Therefore, if you calculate this A, it will become average of I square divided of square of average of I. So this I square average is always greater than or equal to average square of I. This is the way I square average minus I average square is what is called the variance in I. And you can show that this I square is always greater than or equal to I square. So with suspecting light's intensity to be varying in time, we have come to a situation something like this. Detailed calculations show that one can get A is equal to 2. Using this and using perturbation theory, people are, physicists were able to get the answer A is equal to 2. By getting this answer A is equal to 2, what was answered? The detector problem was answered, right? So the mercury light has unstable intensity. Using this theoretical calculation agreed with experimental result. In fact, later laser light was used. When later light was used, you know that laser light has, a constant magnitude in a way, right? So its intensity can be much more, not as time varying as the other one. So for laser light, A turned out to be 1 in this experiment. Since the laser light has stable intensity, I square is same as I square, so A is equal to 1. So we were able to solve the detector problem, but the problem of whether light is photon or not, so still no proof of photon. For photon, the result should be A is equal to 0. So reason for failure to see photon. Quantum notion of eigenstate is needed here. So now they are suspecting that not only the intensity of light changes in our experiment, we have to look at the very nature of light in a beam. So they started suspecting the beam itself. According to QUT, there are different states of light. Maybe Professor Umesh said coherent states he will refer to. Actually, the title of my talk is quantum states of light. So there are different states of light. One is number state of light. The other one is coherent state of light. So there are different types of light, and photon is the simplest quantum state of light. So I am describing that here. So if you go to QED, there are different states of light. How much time is there for me? I may take another 15 minutes. Okay. So some states have definite number of photons, others have indefinite number of photons. So if you say light is coming to me and there is some light beam, if somebody asks you how many photons are there, just because you have a beam of light, you can't say there are definite number of photons in that. For that, let us please take that right now. After this, I may come to that. So when atoms emit, number of photons may not be definite in the beam, right? So how do we get this light? I don't know. We say that light is incoherent and all that. And thanks to so many atoms in that system, they all help us, right? So imagine one atom emitting now and another atom emitting 1 hour later, right? I mean, there would have been darkness everywhere. So somehow there is some unity among this atom. But what is happening is, there, when all of them send the beam of light, that beam of light will not have, so in general, definite number of photons. So far in experiment, in all the experiment I discussed so far, including laser, right? Light is from same transition of many atoms. So what we are experimenting, what Hanbury Brown Twiss experiment was discussed here, it consists of detector, need detection and all that. But all the time, we are not looking at a single transition. We are looking at a multitude of transition. We get a beam and we send that beam to two detectors. So if photon is to be identified, if there is photon, so then one has to look for a particular transition of a single atom. So then that you should check whether that particular transition consists of wave or particle nature of wave. So that is the final conclusion of all this discussion. So Grangier, Roger and Aspect, they did the experiment in 1986. 1986. Imagine 1900, Planck gave the quantum hypothesis. The real quantum photon, was already familiar to us. We have used photon nature to explain photoelectric effect, Compton effect, everything. Even Compton effect can be explained using semi-classical theory. So this experiment in 1986, they wanted to choose a particular atom because what was needed? If at all you want to check whether light consists of photon or not, you have to pick only one single transition, not many, right? All these earlier attempts were like, most of you know Kannada. ಹುಲ್ಲನ್ನ ಟ್ರಕ್ ಹೋಗ್ತಾ ಇದ್ರೆ ಅದಕ್ಕೆ ಸೂಜಿ ಸಿಕ್ಕಿಸ್ಬಿಟ್ಟು ಹುಲ್ಲಲ್ಲಿ ನೋಡ್ಕೋದು ಅನ್ನೋ ಸಮಸ್ಯೆ. Like you put a needle in a haystack and try to figure, later research where it is or something. So this calcium atom can be excited from ground S state to a high lying S state, top one, by some laser pumping, optical pumping. Once you do that, it decays to an intermediate P state. Some red light comes, say, low energy. And suddenly, after it decays to P state, suddenly the P state gets down to the ground state back. This is a sudden, within a short time, it comes down to ground state. So, what the experiment done by GRA, right? They took this calcium atom, that black dot, the first transition from the higher excited state to the intermediate level. They sent it through a photomultiplier tube, some detector. That is the first transition. The second transition later, right, that was sent to this detector system. So nu1 and nu2 are single transition of a single atom. nu1 is sent as trigger to PMT3. I will tell you what is the trigger, but only theoretically. I am not an experimentalist. I don't know how triggering is done. nu2 is sent to beam splitter, later makes PMT1, PMT2. These are photomultiplier tube. There is a coincidence counter. nu1 triggers the other two photomultiplier tubes to get ready to receive nu2. So as soon as the first transition goes, this photomultiplier tube then produces a signal, and that signal reaches, say, the coincidence counter, from which an information is sent to D1 and D2. Don't switch on. Now get ready, right? Don't try to count. Only count after I come here or after this signal comes. So they say the new one triggers the other two PMT to get ready to receive new two. Otherwise, be off in the off situation. Hope you understand. That is triggering. So maybe Professor Umesh has got better knowledge. This is how we theoreticians speak. We have no, limit for extending our ideas. Right? We can say anything can happen like this, right? It is all the experimentless. Experiment was done for anti-coincidence with weak source. Here I have told weak source. I should have told it from the beginning. All along they used weak source. Result, there was no coincidence, and PC was 0, and A was got as 0. So photons at last. So this is. So this is the only book which I have referred to, The Quantum Challenge, Modern Research on the Foundations of Quantum Mechanics, George Greenstein and Arthur G. Zazank. So this book is available free also. So you can read this book, and I thank the chairman and the department and the yes now for this lecture, and thank you for your patience. If you have any questions, yes, please.
Sir, you mentioned photoelectric effect can be explained from wave theory. So the black body radiation problem. So can that be also explained from wave theory of light?
The problem becomes in black body radiation, we are worried about the nature of light, right? How light is. I can continue and say that this is semi-classical treatment. We treated atom quantum mechanically, but the field as classical. You know that after Schrodinger's quantum mechanics, relativistic quantum mechanics came. It explained hydrogen atom energy much better. But there were problems even with Dirac's description. So one had to go beyond that. So Dirac used relativity to explain that. So the next step was, so we have seen how to quantize material particles. We are not getting two results which could not explained by Schrodinger quantum mechanics and also Dirac quantum mechanics. One was the lamp shift experiment. So lamp shift could not be explained by Dirac's theory. The second one, the spontaneous emission of light. This could not also be explained, right? Although he was the first to explain antiparticles, right? Dirac's theory. So because even relativistic quantum mechanics did not explain this, then they thought, why not look at field also quantum mechanics? So the field was treated quantum mechanics. According to the quantum treatment, you have, light behaving like waves also in certain situations. Laser light itself is a good example. Coherent states and number states are these two. The number states of light have number definite, but the phase is indefinite. In coherent state, the phase is definite, the number is indefinite. So light can be in wave form also and quantum form also. Okay.